Hello, everyone. I'm Peihao, graduated from the University of Oxford, supervised by Professor Clive Sevier. It's a great honor to talk about my PhD research, thermomechanical coupling during large-scale deformation of polycarbonates through DYMAT 2024. This presentation will be divided into following parts: my motivation, experiment techniques, and research topics. Finally, I will give the short summary. The plastic market will experience a dramatic increase from 2021 to 2030 due to the lightweight design demand from automotive, protective equipment industry. And however, the impact behaviors of polymer are not well understood. That's the reason why our industrial partner sponsors us polycarbonate, polyisoisone ketone, and polyamide 6 to understand impact behavior of this polymer and their composites. There are several scientific challenges to measure the high rate response of polymers and its composites because they are low impedance, particularly for composite material, because the homogeneous material properties it's quite difficult to get very accurate constitutive behavior of composite material. Another key challenge is to understand the constitutive behaviors in adiabatic loading. We know the polymer material is quite temperature sensitivity, and in adiabatic loading, the temperature cannot be dissipated into the environment. It can cause the stiffness and the stress get very evident reduction. So how we evaluate this heat, how we understand the heat effects during the adiabatic loading. This is a key challenge and a main topic for my PhD study. Here is the research team. So this is a joint project. Oxford take charge of the experiment and Nottingham take charge of the numerical thing. I started my PhD by doing large-scale tensile tests on polycarbonate. I developed several novel rate and temperature-dependent tests on polycarbonate. I have used high-speed optical and air camera, and I went to ESRF to perform in situ high-speed Hopkinson bar test to observe the deformation and failure process of the composite material. Then I transferred my data to Nottingham team. We would like to involve of adiabatic into OGR, Oxford glass rubber model. The Oxford glass rubber model performs best to simulate the polymer around its glass transition temperature in past 20 years. Now we want to add more adiabatic impact stuff into that model. To date, this model can match the 1D stress state quite well. The final aim of this project is we want this model can predict the test with more complex stress state, such as dynamic three-point bend and Tyler impact test. Since the successful of my PhD project, we got two follow-on projects were funded by the same industrial partner, carbon dioxide derived polycarbonates, and funded by US Army to investigate the dynamic fracture behaviors of polycarbonate. The experiment techniques what I used in my past 4 years is screwdriver machine for quasi-static test, hydraulic machine for medium rate test, and split Hopkinson bar for high rate test. I developed a long split Hopkinson bar to characterize this material at a very large strain. Some additional measurement techniques here, the high-speed error camera, thermocouple, and high-speed camera and digital image coloration. Again, I went to the ESRF to perform ultra-fast in situ accuracy with split Hopkinson bar. Now, I start my PhD by doing large-scale tensile experiment, which is very relevant to industrial demand. Everyone use that to examine their material. In my test, the CCD camera was put in front of the sample and error camera backside, which can provide me the stream mapping and the displacement mapping. And error camera gives me the temperature rise mapping. In this work, I redefined the use of the tensile test for material characterization and how we understand the strain localization during that test. Here is the digital image coloration mapping. I put a 9 data point in the gauge section and another data point called neck. It means the neck was occurring at this area firstly. And if we see the axial true string versus the time curve, here is a zoom in image. We can see the data point called neck or data point quite close to neck just go up directly. And the rest of this data point, the far field point, will experience elastic unloading. So how we understand this string localization and elastic unloading, I built up a FE model. I use the rate and temperature dependent compression data as an input because the compression deformation is quite homogeneous. And then I put that data to this software, generated a DYMAT. I put that DYMAT in FE simulation software. As we can see here, the model overlaps with experiment in force and displacement curve quite a while. However, if we see the local behavior, local true string versus the time curve, we can see the experiment study doesn't match with the numerical simulation. The consequence here is cannot use only this information, global behavior, to extract the constitutive parameters. So I optimize the model parameters to match the local behavior, and the model here can simulate the axial string quite a while and can simulate the thermal mapping quite a while in shear band formation, unstable neck propagation, and to the stable neck propagation to the end of this test. After performing the tensile test, I performed the mole, rate, and temperature dependent test. Here, the tensile test was based on this material. We received the mole material from our industrial partner. So here is a different molecule with polycarbonate. The melt flow rate means different molecule. They changed that to change the ductile brittle transition. And we also obtained a co-polycarbonate. They want to enhance the dynamic properties of this. In this work, I provide a comprehensive data set of 4 polycarbonates, offer important data on molecular weight and comonomer effects during large string deformation. So here is the quasi-static test at varying temperatures from -60 to 120. If we decrease the temperature, we can see higher yield stress. And here is the rate-dependent test. If we increase the rate, we can get higher yield stress, which is we call time temperature equivalent at small string region. So how about the large string region? It brings me to the next work, coupled thermomechanical effects at large string. Here, if we compare the rate-dependent test with the temperature-dependent test from string rate at 560 and 700, we compared with the low temperature test with the same or similar yield stress, we will see very evident thermal softening at large string. However, for the higher string rate test, 3000, compared with -60 Celsius, we didn't see evident thermal softening. To answer why is less softening in higher rate test, I performed the series temperature rise measurement during the different loading scenario and use a model developed by Nottingham team to understand that. The literature measures the temperature rise in past 2 decades. People mainly use the thermocouple and air detector to measure that. The biggest drawback of these 2 techniques is they cannot provide a visualized thermal image. So we don't really know what really happened in Hopkins-Senbar test. In my measurement, I measure the temperature rise through the air camera, and then I calculate how plastic work converts to the heat, which is called Tyler-Quinn coefficient. Here is the temperature rise measurement in my study. Although we have the very high frame rate thermal camera, we cannot get the continuous high quality thermal image. So in here, I developed a new method. I controlled the triggering pressure during the Hopkins-Senbar test. Enables me to get a very similar stress string curve from 7 tests. And I changed the triggering time of the air camera to make sure I can get the IR signal of the air image of thermal data point at different stress or strain. And I use time axis to shift them so we can get the sequence high quality thermal image and the sequence thermal data. I calculated the Tyler-Quinn coefficient here. The lower string rate, I can get a continuous thermal image, and the higher rate, I get data point. The result here is the teleclinik coefficient is also changed with the change of stream. Here is the model. This model can separate the mechanical work into dissipated, conformational, structural, and elastic energy. And this model can simulate the quasi-static, medium rate, and high rate test well. The answer why is less softening is, in high rate test, the side chain or the second motion of the polymer will be fixed. So more percent conformational energy will be needed to fix that chain. So less heat energy will be generated. So less thermal softening. After we understanding what really happened during small and large strain for the polycarbonate, I characterize thermomechanical properties of polycarbonate composite. Here is a 20% short glass fiber reinforced polycarbonate. I applied a set of two to this heterogeneous material and investigate the thermomechanical properties. So here is a rate-dependent test at quasi-static. Not surprisingly, the higher strain rate gives you higher yield stress, but at the higher strain, we can see the EMATS2 beyond 0.5 per second test. The reason is, in EMATS2 test, we can get only 2 Celsius temperature rise. However, for the 0.5 per second, the temperature rise is about 30 Celsius. So that's the reason here causes the thermal softening for 0.5 per second. Here is continuous thermal image. I just put some here. We can see the strain localization or temperature localization at the beginning, and the temperature difference between maximum and mean is 2. Or with the end of this test, the difference between these two is 1 Celsius. Again, for the medium rate test, we can see the localization at the beginning and the difference between maximum and mean is 8 Celsius. With the end of this test, we can get this difference is 4 Celsius. It is because this temperature was transferred to the surrounding material, and then we get the homogenization at the temperature mapping. Again, I use the same method to characterize this material at the high strain rate. As we can see, the stress drop at 0.6 true strain. From the temperature rise mapping, so from the thermal image, we can see the localization at the beginning, and then shear band formation. At the end of this test, we will see the maximum temperature is above the 150 Celsius, which is beyond the glass transition temperature of the polycarbonate. So that's caused the softening. After testing, I collected the test sample. We cannot see very evident crack or failure. So I took the sample to ESRF to do the measurement. Through that measurement, we didn't see any failure or debonding during the in situ X-ray measurement. It brings me to the summary of my research. My research started by doing large strain tensile tests using digital image coloration and infrared techniques. I use rate and temperature dependent compression tests to understand the experiment observation during the tensile test. The consequence is we can not only use the global behavior to examine the constitutive parameters, we should think about the local behavior, such as local true strain versus time curve. And through this study, I validate the temperature time dependence at very small strain and understand the molecular weight and comonomer effects during different loading conditions. To answer why it's less softening at large strain at high rate, I did a lot of temperature measurement. And the consequence is that the teleclinik coefficient is not a consistent value. The molecular transition plays a very important role in energy distribution. After that, I applied the set of two for thermomechanical characterization of composite material. The result shows that adiabatic heat is essential for the large strain behavior. So the achievement of my study is I use the advanced technique such as high-speed infrared camera to observe deformation process of polymer and impact loading. And this data set can use for the model development and the impact loading. And this gives the insight to industrial partner for the next generation high performance polymer product. I would acknowledge my sponsor, industry partner, and the research team who support me to be here. Thank you very much.